Hey guys, I'm sorry this is so late. This is the assignment I did with A group, the notes in the assignment I did with A group on Monday. That would have been October October 26th, this past Monday. The power went out and everything, and I was helping family members, stuff like that. I just never got a chance to sit down and record this, so here it is. This assignment will not be due until this coming Thursday, just to give you all some time, especially those of you without power, give you some time to actually work on it. But if you get the chance to, watch this before tomorrow, because tomorrow in class we will do another assignment over this. So this is 6.3, simplifying square roots using the product property. So using properties of radicals, a radical expression is an expression that contains a radical. Go figure. An expression involving a radical with index n is in simplest form when the following three conditions are met. So what I mean by index is if we have a radical, this little number right here is called the index. So if it's a square root, that number is understood to be a 2. If it's a cube root, that number is a 3. Fourth root, it's a 4, so on and so forth. It just tells us which root we're taking of our radicand. Our radicand is the number that is actually under the radical. So the n is the index, the x is the radicand. So an expression involving a radical with index n is in simplest form when these three conditions are met. No radicands have perfect nth powers as factors other than 1. And I'll kind of explain that here in a second. And remember, the radicand is the number under the radical, or in the radical. No radicands contain fractions, so I can't have a fraction under or inside my radical. And then no radicals appear in the denominator of a fraction. So I can have a radical in a fraction, I just don't want to have a radical in the denominator, so the bottom of the fraction. And then we can use the property on the next slide to simplify radical expressions involving square roots. Before we do that though, I want to talk about this first point right there. The first point. No radicands have perfect nth powers as factors other than 1. Today we're dealing with square roots, so this will be no radicands have perfect scratch what I just said. I'm going to try to explain it a little different. We have numbers that are called perfect squares. If I do 2 squared, that gives me 4. 3 squared gives me 9. 4 squared gives me 16. 5 squared gives me 25. 6 squared gives me 36. So on and so forth. Everyone should know that. That's just squaring numbers. These numbers that we get, the numbers that I'm circling, those are what we call perfect squares. If I take the square root of 4, I get back to 2. Take the square root of 9, I get back to 3. Take the square root of 16, I get back to 4. 25, get back to 5. Square root of 36, get back to 6. So those numbers that are circled we call perfect squares because they give us a nice whole number when we take the square root of them. So that's what this first point is saying. No radicands have perfect nth powers as factors other than 1. So that means I don't want any of these numbers that I've circled underneath my radical. Because if I do, I can simplify it further because I can take the square root of those numbers. Hopefully that explanation makes a little bit of sense, but let's just look at the rule and then we'll jump into some examples. So, here is our product property of square roots. The square root of a product equals the product of the square roots of the factors. So this should actually start off with the square root of 45. If I have the square root of 45 and it wants me to simplify it, I need to try to see if I can find any perfect squares that multiply to give me 45. And I would like to find the biggest perfect square that multiplies to give me 45. In this case, it is 9. So that's the first part of this right here. I can break 45 down into 9 times 5 because 9 times 5 equals 45. If I have a product underneath a radical, I can then split it into their own radicals. The square root of 9 times the square root of 5. That's our product property right there of square roots. Now I know what the square root of 9 is. Remember, 3 squared gives me 9. So if I take the square root of 9, I get 3 back. 5 is not a perfect square. I cannot take the square root of it. There are no perfect squares that go into 5. So 3 square root of 5 is the simplified version of the square root of 45. So here's our little algebraic rule down here. Square root of AB equals the square root of A times the square root of B, where A and B are both greater than or equal to 0. So we're essentially just finding the biggest perfect square that goes into our number under the radical, breaking it apart like this. That way we can take the square root and simplify it. Hopefully that makes sense, and hopefully doing more examples helps you better understand it. So let's jump into our examples. So our first example is the square root of 108, and it wants us to simplify this radical, the square root. So like I said on the previous slide, what I'm essentially doing is finding the biggest perfect square that goes into 108. So we know our perfect squares are 4, 9, 16, 25, 36, 49, 64, 81, 100, so on and so forth. They just keep going and going and going. So I'm just going to start dividing 108 by all of these perfect squares, starting from the biggest, going down to the smallest, to see which one, the biggest one, goes into 108. So 108 divided by 100 gives me a decimal, so I know it's not 100. 108 divided by 81 gives me a decimal, so I know it's not 81. 108 divided by 64 gives me a decimal. 108 divided by 49 gives me a decimal. 108 divided by 36. 108 divided by 36 gives me 3. So I know I can break 108 down into 36 times 3 underneath my radical. Based on my product property of square roots, I know I can take the square roots or the product and separate them into their own square roots, just like that. Now I know the square root of 36 is 6. So 6 times the square root of 3. Now I just need to double check. I need to ask myself, are there any perfect squares, any of these numbers over here, that go into 3? The answer is no, so this is my simplified expression. Hopefully that makes sense. So let me erase this stuff and give me some room for part B. So letter B, we have the square root of 9x to the third power. So once again, we have 4, 9, 16, 25, 36, 49, so on and so forth. There's all my perfect squares. 9 is a perfect square itself, so I don't have to break it down into anything. I can just take the square root of 9. Now I need to break x to the third down into something that I can take the square root of. If I take the square root of x squared, that just gives me x, because x times x gives me x squared. Also, a little trick, here's our index. If we have a square root, it's understood to be 2. If I take a square root of something with the exponent, I just divide the exponent by the index. So x to the 2 divided by 2 gives me x to the first, which is just x. So if I had the square root of x to the 8th, that'd be x to the 8 divided by 2, which gives me x to the 4th. That's just a little trick we are able to use with square roots. So I can break x to the third down into x squared times x. Because if I multiplied those, that'd give me x to the third. And now I've broken it down into something that I can take the square root of. So the square root of 9 is 3, so I pull that out of the radical. Square root of x squared is x, so I can take that out of the radical. And then I cannot take the square root of just x by itself. So here is my simplified expression. I know this can seem kind of confusing, especially if you're not in class to ask questions, but try your best. And you can ask questions whenever we get back to in class. So jumping into some more examples. Number 1, we have the square root of 24. So I'm asking myself, what's the biggest perfect square that'll go into 24? Well, that would be 4 in this case. The only other perfect squares would be 9, which does not go into 24. 16 does not go into 24. 25, that's bigger than 24, so that's all we can look at. So 4 is the biggest perfect square that goes into 24. Square root of 4 gives me 2. Square root of 6. There are no perfect squares that go into 6, so I know this is my simplified radical. Let's look at number 2. Negative square root of 80. This is like a negative 1 outside my square root. So I'm just going to bring down the negative as I'm working this out. So I've got to ask myself, what's the biggest perfect square that goes into 80? It is 16. It's the biggest perfect square that will go into 80. 16 times 5 gives me 80. So when I'm taking the square root of 16, I keep this negative outside. Square root of 16 is 4. And then the 5 has to stay under the radical because I didn't take the square root of it. There's no perfect squares that go into 5, so I know this is my simplified answer. Number 3, we have the square root of 49x cubed. Once again, this one's nice, kind of, because 49 is a perfect square. So I can just take the square root of 49. And then just like we saw on the previous slide, we can break x to the third down into x squared times x. Square root of 49 gives me 7. Square root of x squared gives me x. I can't take the square root of x, so it stays under the radical. And there's my simplified answer. And let's look at the last one. Square root of 75 into the 5th. The biggest perfect square that goes into 75 is 25. 25 times 3 gives me 75. And then I need to break into the 5th down into something that I can take the square root of. So I can break it down into the 4th times n. So taking the square root of 25, I get 5. Done with that. I can't take the square root of 3, so that's going to stay under the radical. For the square root of n to the 4th, we can use our little trick. 4 divided by 2 gives me 2, so I get n squared for the square root of n to the 4th. And then n I cannot take the square root of, so it stays under the radical. So outside of the radical, I get 5n squared times the square root of 3n. So there would be my simplified expression. Now there is another way we can approach it. I don't like this method quite as much, but if it makes more sense to you, then I'm fine if you use it. So let's look at this last example again. Square root of 75 n to the 5th. Yes, that's the correct thing I'm looking at. I hope you guys remember factor trees, breaking it down into its prime factorization. So I can ask myself, what times what gives me 75? 3 times 25 gives me 75. I can't break 3 down any farther besides 1 times 3. So that's a prime number. And then I can break 25 down into 5 times 5. So the prime factorization of 75 is 3 times 5 times 5. And then I have 5 n's right here, so n. This is the square root, so that index is a 2. So when I break it down into my prime factorization, a little trick I can use is I'm looking for pairs of things underneath the radical. So I have a pair of 5's here, pair of n's, and another pair of n's. If it has a pair, I can pull it out of the radical. If it does not have a pair, it has to stay under the radical. So 3 does not have a pair, so it stays under the radical. 5 has a pair, so it can come outside the radical. N has a pair, so I can pull it out of the radical. I have another pair of n's that I can pull outside of the radical. My last n does not have a pair, so it has to stay under the radical. 5 times n gives me 5n squared times the square root of 3n, and that gives me the same answer I got on this slide. So that's another way of looking at it. I like this method better because I feel like it goes a little quicker. It's not as much writing, but I'm fine if you do it either way. So if you like this way, just look for pairs. If it has a pair, it can come outside of the radical. If it does not have a pair, it stays under the radical. So hopefully that all made sense. If not, you can ask questions in class. So our assignment is page 297 in your textbook, numbers 5 through 20 all. And that'll be due, like I said, Thursday. That would be November 5th. And it'll be due on Canvas for everybody. So, if you're in A group and you've already finished it, great. I'm about to open up the assignment on Canvas here pretty quick. I haven't opened it up yet, but that'll be due on Canvas by Thursday, November 5th at 11:59 p.m. Like I said, sorry it's so late for posting this, but you guys have time to complete it and watch this video. I'd like for you guys to watch this before class tomorrow, because I'm not going to be in class tomorrow, and you guys are going to get another assignment over this. So please watch this if you can. And you can ask questions on Tuesday in class. Y'all have a great day.